The purpose of this lab was to observe the motion of a mass oscillating as it swung from a spring in an arc, construct a computational model using Newton's second law to fit the data, compare the predicted and observed positions of the mass over time, and see if the system satisfied the energy principle. The video of the motion was provided, so all I had to do was record the position data in Tracker in order to start my analysis. After doing this, I had to calculate the spring stiffness constant and original length of the spring based on the observed data. From here, I created multiple models in VPython using Newton's second law to predict the motion of the mass based on the assumption that the net force consisted solely of the force of gravity due to the Earth and the force due to the spring, and then compared the observed positions with the predicted positions to find that the model created based on the oscillations of the x position was most accurate. However, all models, including this one, became less accurate as time increased, indicating that there was another force acting on the mass, slowing it down. After calibrating the length scale and choosing my coordinate axis, I started tracking the position at the beginning of the video clip, which seemed to be a few fractions of a second after the mass was let go of, but I couldn't be too sure because of the poor quality of the footage. From here, I exported the position to a CSV file, which I used later in my comparison. Then, I started working on the computer model. There were two significant forces acting on the mass, the spring force and the gravity force due to the Earth. My model took both of these and only these into account when estimating the net force. The gravity force was constant throughout, but I had to recalculate the spring force at every time step, since it changed depending on the direction and stretch of the spring. To do this, I had to calculate some properties of the spring, such as the spring stiffness and the relaxed length L naught based on my observations. I needed to use the formula T equals 2 pi times the square root of m over k, where T is the length of one period, to calculate K, the spring stiffness. However, there were two possible values for the period, because there were two oscillations, the x position data and the y position data. After calculating the values of the spring constants for each of these estimations, I had to calculate the uncompressed spring length, L naught. To do this, I used the fact that when the mass was not moving and the spring was at a length of 0.7 meters, the magnitude of the force of gravity equaled the magnitude of the spring force. The gravity force was simply mass times gravity, and the spring force was the spring constant times the difference between the stretched and relaxed length. I solved for L naught with each spring constant and then put these values into my Python code to construct two different models. I knew the initial position from the tracked data, and the initial velocity was 0 since the mass supposedly started from rest, so once I had the net force, I could predict the velocity and position at each time step using Newton's second law, just like in the first two labs. Running the two simulations provided these data. Then, unlike in the other two labs, I read the observed data into the model from the CSV file I had originally copied it into. This allowed me to view the observed and predicted motion at the same time and easily visually compare them. The first time I compared the two sets of data, the two lines looked very similar, but translated significantly away from each other. This is probably because in my model I set the initial velocity to 0, but I think the provided video starts a few time frames after the mass was let go of, meaning it didn't actually start from rest. This meant the model was behind what it should have been. For this reason, I changed the time parameter slightly in order to account for this, and when I ran the model again, it fit the data a lot better. The blue ball is the model and the red ball represents the actual mass. As you can see, this model, based on the x position data, is fairly accurate at the beginning, but as time increases, it becomes less correct. If we examine the graphs of the x and y position based on this model, it is evident that the x data is accurate at the beginning, but over time the predicted x positions occur at later times than the actual x positions. The y positions are fairly accurate throughout in this model. However, the only major difference in the data is the wavelength of the oscillations, which in the observed data seems to decrease in length. The amplitude was accurate throughout. The discrepancy in the x positions is probably due to the fact that the model assumed that the only two significant forces were the force due to gravity and the spring force, when in actuality there were other forces present that would affect the motion, namely the drag force, which opposed motion and thus probably slowed down the mass over time. Another way to explain the discrepancy is to use the energy principle. According to the energy principle, the total change in energy of the system is equal to 0 if there is no interaction with the surroundings. Looking at the entire spring, mass, and Earth as the system, one can say that the total energy change is 0. Total energy change is the sum of the kinetic energy change and the potential energy change of the system. The kinetic energy change of the system can be calculated using the formula kinetic energy equals 1/2 mass times speed squared, since the mass and speed of the ball at each time step are known. The potential energy of the system can also be calculated using the two formulas gravitational potential energy equals mass times gravity times height, and spring potential energy equals 1/2 times the spring constant times the extension squared. I entered these calculations into the code and ran the simulation again, this time plotting the kinetic energy, gravitational potential energy, spring potential energy, and the total change in energy. As can be seen by this graph, the total energy change is 0 throughout the oscillations of the mass, indicating that the energy principle is satisfied. It is slightly off, but this is probably because the kinetic and potential energy changes of the spring itself were not taken into account. However, this is a simplified version of the energy principle. The actual change in energy is equal to the sum of the change in kinetic energy, the change in potential energy, and the change in thermal energy. As energy is transferred between potential and kinetic energy as the mass moves, some of it is lost as heat, so the total energy change is not exactly the sum of the change in potential and kinetic energies. The model assumes that there is no energy converted to thermal energy, but this is not true in actual observed motion, which is also a possible explanation of why the model became less accurate as time increased. Finally, I repeated the aforementioned steps using the spring compression constant and relaxed string length calculated using the oscillations in the y data value. As can be seen by this graph, both the x and y position data are very similar in wavelength and amplitude in the model and the actual motion towards the beginning, but they both become less accurate as time progresses. It is interesting to note that the model constructed using the x data oscillations was actually more correct over time with the y position data than the model constructed using the y data oscillations. However, this completely disregards any energy lost from the mass as heat, which we know does occur occur, so it's probably not completely precise either. Overall, one must remember that the model is only as accurate as the assumptions made, and in this lab, it was assumed that air resistance was not a significant force acting on the object. It would be important to take the drag force and the conversion to thermal energy into account when actually using such a model to predict spring motion in cases like extreme sports, when even small discrepancies over time can be significant and affect safety.